Yo, what up, everyone? It's your boy, Mr. Oldridge, aka ChemistNate, coming at you with another banger. Today's banger is, me trying to answer your organic chemistry questions. Do I have any confidence in my own ability here? The answer is no. We do have a question that has appeared here from BIA. BIA is here, it looks like. Now, this isn't necessarily exactly organic chemistry, but that's still okay. It's the only question we currently have. Just chilling. If anyone has organic chemistry questions, here he goes. Okay, yeah. This question isn't organic, which is why I'm confident about it. I just want to reiterate how not confident I am about actual organic chemistry. But hey, whatever. Okay, we got a sample of urea, CH4N2O, and it's 86% pure. We want to know how much of that sample is nitrogen, given that there is no nitrogen in the impurities. Okay, so here's the idea. What we have is 86% of CH4N2O and 14% of something else, and we don't know what it is. So all we really need to know here is what fraction of this 86% is nitrogen. What fraction of the 86% is actually nitrogen? Now, I'm not asking about number of grams here. I'm asking for the fraction, or the, I guess it's kind of percent of the total mass of urea that is nitrogen. You may have a formula for percent composition. The percent of nitrogen in this sample is the total molar mass contribution of nitrogen in that sample out of the molar, and I minimized it, out of the molar mass of the entire molecule itself. Most teachers will write the word molecule here. Now, how do you calculate molar mass? Oh, that is not what I wanted to do. Thank you. The molar mass of the molecule is the sum of the atomic masses of each of the atoms. The teacher I co-teach with asks kids to write down what the atoms are, and I'll do that here for you. It's 1 carbon, 4 hydrogens, 2 nitrogens, and 1 oxygen. So their molar mass is 12.01, and 4 1.01s, that's the atomic mass of hydrogen, 2 14.01s, and a 16.00. BIA, I hope you understand where those numbers are coming from. Those are the atomic masses off of the periodic table. And then you actually have to add those up to get the molecular mass. 12.01 and 4 1.01s and 2 14.01s and a 16. The molar mass of urea is 60.07. Most teachers will put that in a unit called grams per mole, but you're allowed to put it in AMU as well. That's atomic mass units. Now, what fraction of this molecule is actually nitrogen? Well, nitrogen's contribution was 2 14.01s out of the total of 60.07. More explicitly, out of the total 60.07 grams that every mole of urea weighs, 28.02 of it comes from nitrogen. What we're actually calculating here is the percent composition of urea, more specifically the percent by mass of nitrogen in urea. 28.02 divided by 60.07 is 0.466455. I'm carrying a lot of decimal places here. almost too many. And what that means is that 46.6455% of the 86% is actually nitrogen. You're allowed to multiply these percentages by each other, because 86% is already, for example, per 100 grams of sample. That's what percent means. 46% of 86% ends up being 40.115%, and when you round that off, you get about 40%. So, urea is 46 or 47% nitrogen, and so 46 or 47% of the 86% of the whole sample is also nitrogen. So your final answer here is about 40%. Someone in the chat said 28%. Perhaps they were thinking of the 28 that came from here, but that was fake news. Anyways, we've got some people here. Ozonolysis of an alkene. Mayer. Oh yeah, Mayer is here. Ozonolysis of an alkene and an aldol condensation. Okay, so let's see what we got here. Ozonolysis of alkene. Now, you might be asking for two separate things. It's like, what are the products when you make it? Or what is the mechanism of it? I'll go over both of those for you, but I'm just going to steal the mechanism from somewhere online. Overall, I'm going to use an equal sign here for the double bond. I hope you understand. I'm sure you do. That's what an alkene is. Can react with O3. And I believe what ends up happening is that the O3 breaks the double bond. And I'm going to show it breaking here. And both sides of the molecule stay the same. So you fracture it right along there. I'm preserving the double bond because I know what's coming. And then all you actually do is you replace whatever the rest of the molecule was with O. So you end up in this case with two aldehydes, but it could have just as easily become a ketone, maybe even a carboxylic acid. I'm sure you probably knew that, and I haven't shown any of the byproducts here. I honestly forget what they are. The mechanism itself is much more interesting. Let me go see if I can track that down for you. I'm going to try to track down a copy of my favorite organic textbook called Instant Notes in Organic Chemistry. I know I have this PDF somewhere. Whatever. I'll just grab the ozonolysis mechanism. Maybe explaining it and hearing it from me about what's attacking what will help. We'll do the same for aldol condensation right after this, thanks to a request from Pratyesh. I hope I'm getting these names right. Lots of people saying hello. Oxidative ozonolysis of terminal alkene. Yeah, we can work on that in a second. That one's gonna be pretty similar, I would have thought. Oh, are you supposed to use dimethyl sulfide? Oh yeah, you need that reducing agent. Break it apart, crack, crack. There you go. Okay, got it. Kind of like this one. Please don't be an SVG. It's an SVG. That's too bad. Whoops. Not what I wanted. There we go, that's what I'm talking about. I'll steal this eventually. I missed it. Okay. Step 1 is very likely understanding what the Lewis structure for ozone looks like. Ozone is not a triangle, it is kind of a bent molecule the same way water is, except it only has one lone pair on the central O. You can't draw a Lewis structure for ozone that doesn't have formal charges on one of the atoms. It's actually impossible to draw that Lewis structure. Therefore, you have a plus and a minus charged O somewhere inside that molecule. Now again, that's a formal charge. The fact that there are extra electrons around one of the O's is what gives it more negative charge density. So if there's slightly more charge density in one area, there's probably slightly less in another area. That's the definition of charge neutrality or whatever. So there is a positive portion of this molecule that the double bond can attack. I don't know if you've ever seen an alkene mechanism attacking a Br2 molecule or a dihalide. London dispersion forces, like the repulsion of the electrons in the Br2 bond, just from them simply coming near these electrons, makes one of the bromines slightly positive and ripe for attack. You can think about this doing it similarly. And because of the shape of the molecule, if it collides with the alkene at this angle, there will be a repulsion between these electrons and some of the electron density in the molecule, making that portion of the molecule ripe for an attack. The double bond of the two carbons will attack one of the oxygens, preferably the one with the double bond in the Lewis structure. You'll have to push one of the electrons in the bond onto the positively formal charged oxygen, but hey, that just makes it a formal charge of neutral, finally. And the minus charge on the next oxygen in line can attack the carbon that has lost some electron density because those electrons went and attacked the oxygen that was positive charge. The most important thing about organic chemistry that I can get across to you is that all of the mechanisms are about you pushing electrons towards positive charges. Taking minus charged areas, or electrons in bonds, or even lone pairs, and pushing them towards whatever happens to be positively charged. Just throwing it out there. Took me a while to really catch on that that's what was happening. These electrons are attracted to that O. These electrons are attracted to that carbon once those electrons begin attacking this oxygen. It's like a concerted reaction here. And you end up making this ring. I've never heard it called a molazonide. Never in my life, but that's not the point. And then the sigma bond between these two carbons can move basically in the same direction. And if you're asked to draw the mechanism of ozonolysis, just want you to remember that the electrons in the breaking of the molecules put the arrows in the same direction in both cases. I don't think it actually matters, but it'll help you have confidence in your knowledge of the mechanism. Push that sigma bond into the CO. Well, it's currently a sigma bond, but it becomes a pi bond. You'll have to break the next sigma bond in the chain, bam. And you'll want to form a double bond here as well, because this carbon cannot handle having only 3 bonds. I don't really remember seeing this when I learned the mechanism of ozonolysis, but hey, that's the way it goes. This just looks like a regular peroxide style reaction, and maybe you want to think about this as an oxygen peroxide, who knows. One of the O's is double bonded to the carbon. It's almost done. Seems almost done. And then this carbon is also already double bonded to the oxygen, but has one extra sitting on it. I feel like that's going to be easy to remember. One of those has to have the extra oxygen on it. The fragments can recombine to form the ozonide. That's fun. This reminds me of a Diels-Alder cycloaddition, even though it's not exactly the same thing. You've got two alkenes reacting to form all single bonds. Those electrons in the pi bond are ripe for attacking that carbon. That carbon is slightly positively charged because it's connected to an electronegative atom. I think you could call this a nucleophilic attack if you wanted to. This carbon is kind of a nucleus. Yeah, that makes sense to me. And as always happens when you attack one of these carbonyl carbons, you'll have to break the double bond with the two oxygens. That oxygen actually wants that electron density because it has a formal charge of +1. And the oxygen with the formal charge of -1 does not mind attacking that carbonyl carbon. Again, with the negative charges attacking slightly positive charges. Wow, there is no mechanism given here. I feel like I've read that this is like a 9 or 13 step process of the actual oxidation. Creating the ozonide is probably where you have to get to. I don't know, I'm just assuming that. It's basically as far as I can take you. What do we have here? We just have some people. We will have requests for oxymercuration-demercuration. And we had a request for ozonolysis of a terminal alkene. Let's go see, because I don't actually know if that's at all different. Is ozonolysis of a terminal alkene any different? I don't know the answer. Well, you are not helpful. Reductive workup. Hey, here's a terminal alkene. Ozonolysis of a terminal alkene creates exactly the same thing. It's not different at all, as far as I can tell. If someone in the chat knows, I'd love to know. We're talking about ozonolysis of a terminal alkene. I'm going to search this entire thing for the word terminal. Ozonolytic cleavage of cyclohexene to terminally differentiated products. Well, that's just a paper that they cited. I had a question where it was a reaction map for turning a generic terminal alkyne into an aldehyde. I was going for using hydrogenation in the presence of Lindlar's catalyst, which would reduce alkyne to just alkene, and ozonolysis. In the answer provided, the alkyne underwent ozonolysis, followed by zinc and acid. The acid, it breaks up the intermediate ozonide, protonates one of the oxygens to make it a better leaving group. Wow, this guy knows more than me. That's not helpful. All the information I can find is that the answer is no. And in fact, the first example I gave here was a terminal alkene. Now again, I'm actually kind of guessing on whether or not that's true facts or not, but it makes sense to me. Let's try one more thing. Ethene plus ozone reaction. Let's see what the people say about this. There's ethene plus ozone. That's great. That's great. Well, that just makes an ozonide, which is just going to be broken up by whatever reducing agent you have. Cool. Yeah. So it's exactly the same thing. You just end up with aldehydes instead of ketones. Well, I guess specifically for a terminal alkene, you get, what's that one called? It used to be called formaldehyde. What's it called now? It's called methanol. Yeah, that's it. That's it. 1 carbon aldehyde. Could Mayor let me know in the chat if that was helpful enough, and if you have any follow-up questions. I'll keep in mind that I can come back to this if worst comes to worst. I just saw someone request the inductive effect. I'm not gonna lie, I don't know anything about the inductive effect. I know I'm supposed to know about it, but I cannot lie, I never actually learned very much about it, other than it helps more oxidized anions, like more oxygens, make something a better leaving group or something. No, that's not it. Yeah, see, I told you, I don't know. Okay. Aldol condensation came up. That came up yesterday. That's why I'm doing this anyways. Then we had an empirical formula question. Saeed Alina Nakvi for the empirical formula question. I'm going to recommend you Google my video about it. I can write that in the chat. Oh, I'm not in the chat right now. Hello, computer. There's your chat. And who was that? Can I at people in this? Good enough. Oh, someone's already answered your question. Ha, whatever. Okay, good stuff. Aldol condensation. I'm reading through. Hi, Nate, you've made things. Hey, you're welcome, Ariana. Oxidative ozonolysis of terminal alkene. I think I've done that. I think. Please let me know. Someone helped you, BIA. Thank you. Okay, yeah, someone helped you and you didn't need me. Oxidative ozonolysis of terminal alkynes. Sure, we'll get there. Someone's just requesting a video about aldehydes and ketones. Yeah, sure, I can do that. Oxymercuration-demercuration. Yeah, that's 2 people who've requested that. What do we mean by precipitate? Someone asked that yesterday. It's a solid that's made when you react to aqueous compounds, almost always. Quantum tunneling? No, I don't know anything about quantum tunneling. I know a guy who knows about quantum tunneling, but I don't know anything about it. Stereoisomers. Do I have any tips to do notes and revision? Not exactly. The way I did not do so well in organic chemistry, but my favorite textbook for this is called Instant Notes in Organic Chemistry. I just found it to be very useful. That's not an affiliate link. In fact, it's not a link at all. And you could probably find it for free online, but you're not supposed to. Paired and unpaired electrons, inductive effect. Someone's headed to med school because of this. Hey, that's great stuff. Paired and unpaired electrons. I don't know if I can help you with that. Stereoisomers came through a couple times. Maybe it's the same person saying it a bunch of times. Okay, so I got 5 things I'm going to cover in that order. If you want to go grab a drink or something while you're waiting for me to get to what you asked for, I don't know, go ahead and do it. So, I have a video about aldol condensations, but I'm not going to lie, I don't remember a damn thing about it. Am I allowed to swear here? I remember I went to Instant Notes in organic chemistry to teach myself this, and then made the video. Like, I'm not giving you anything you can't just look up on your own, but I suppose having someone else talk it through with you might feel special. Oh yeah, aldol condensations, and there's like an acid catalyzed one and maybe there's like 2 different kinds maybe, I don't know, whatever. Let's go see what we got going on here. It's like a reaction video instead of a teaching video. Okay, so here's what I'm learning from this. Oh, there's 2 different things here. So, the aldol seems very clear to me that that's an aldehyde group plus an alcohol group on the same molecule. Wow, it's gonna do that to me again. Alcohol group on same molecule. Okay. It seems to me we're going to start with possibly an aldehyde. It's kind of what it looks like here. Use a base to remove an H on the carbon that is adjacent to the C. Oh my lord, computer. I cannot get ahead of it, apparently. Okay. So you've got a CO group, and then you've got more of a carbon chain, and you have a hydrogen on that next carbon. You've got to use a base to remove that H that is adjacent to that group. The electrons from, in fact, maybe it's more clear if I write that you're removing an H+. The electrons of H's covalent bond will move towards the CO group. And like we saw in the last reaction, CO is going to become C single bonded to O, and that O is going to end up with a minus charge. O is useful for that in that it can accommodate 3 lone pairs of electrons with 1 covalent bond. It ends up with a minus formal charge. And the other thing I remember from my organic days is that after electrons flow or attack the carbon that's attached to the, is double bonded to the oxygen, yes, you have to push the pi electrons into that oxygen to get the minus formal charge. But then later, at some point, that formal charge gets alleviated by coming back down and reforming the double bond. That even happens in esterification, as far as I recall. Then you make an enolate. This forms an enolate. Okay. Enolate is the kind of thing that someone was asking about yesterday with tautomers. The idea that there's another way you can rearrange the electrons here. I still don't actually know what a tautomer is, so maybe I'll shut my fat mouth before I say something I regret. Okay, so base absorbs that acidic hydrogen. The electrons from that covalent bond flow to become a pi bond. And that's possible because the double bond here can be broken to give the oxygen a minus formal charge. I like that. Then you're going to do that to a second version of that same molecule. Ah. This enolate reacts with another of your original reactant molecules. So, how does that attack happen? Oh, it's the same thing that we saw in the ozonolysis reaction. You've got negative charge density here because it's a double bond. It's not like a formal charge of minus, but there's 4 electrons in this space here, right? And the way pi orbitals are shaped, they're popping out at you. So they're going to be attracted to that carbon. Again, with the carbonyl carbon, the C that's double bonded to the O, having a slightly positive charge because it's connected to an electronegative atom, absorbing an attack by a minus charged thing. I like that. I'm going to write that down because I feel like it's been important enough. I think you should practice answering more questions so you would know what you don't. Oh, you're talking to someone else. Ha, nice. Lots of people just talking about stuff in the chat. I like that. I like that. Kenneth Wiley, I regret to tell you that I've dedicated this hour to organic chemistry. I have organic chem tomorrow and I have a lot of chapters. Any advice to study at the last minute? Just practice questions is all I would be doing. I would just download worksheets from other teachers and practice predicting products. That's all you can do. Anyways, this enolate reacts with another of your original reactant molecules. The double bond of your enolate is attracted to the slight positive charge on the original molecule's CO bond. Just like in ozonolysis and even esterification. We're seeing that a lot. Something worth remembering. That minus charge from the oxygen reforms the pi bond between those two as well. Oh, well that's kind of cool. That's all it is. And then the base gives back the H. The oxygen, which gained a formal charge of +1 in the first step, reforms the double bond that it came from. Now you have an aldehyde with a single bonded O minus. This steals back the original H from the base. That's kind of cool. So you just have a bunch of aldehyde, like one reactant, with any amount of strong enough base to rip off that H. You're going to end up with an aldol. That's fun. aldehyde plus, I would venture to call that a Bronsted-Lowry base because it's literally stealing the H away. And you end up with an aldol out of that. Now, the way that Wikipedia is showing this kind of implies to me that there's going to be further reaction. You still have an acidic H that can get stolen away the exact same way that it had stolen the H away in the previous step. You end up with a carbon ion. That's interesting. That aldol still has an acidic H on the carbon, which is adjacent to the CO group. Same as step 1. I didn't number my steps, but whatever. The base can steal it away again, but it leaves a carbon ion. That's a C with a lone pair of electrons and a formal charge of -1. What does it propose happens? Oh, it proposes that it moves into a pi bond and the OH becomes a leaving group. The OH of the alcohol group is a good enough leaving group for the lone pair on the carbon ion to displace it. This forms a pi bond / double bond between the two carbons. Not gonna lie, really don't know how useful that was. I just looked at a mechanism and then explained each step of it to you. Still better reaction than SS Sniper Wolf, though. You end up with an alpha-beta unsaturated aldehyde. That's cool. Alpha carbon, beta carbon. So you end up with that double bond there. I like it. That's ripe for a Diels-Alder cycloaddition as well, almost. Except it's an oxygen, so it's not going to happen. I like it. We got 12 viewers. It's probably because we're talking about organic chemistry. What do we have here? What do we have here? Ah, this is cool. I love you all. You're all good people. Not sure if that helped with the aldol condensation or not. Perhaps we could do a couple questions about it later. Oxymercuration and demercuration. Not gonna lie, I also learned this right when I did my video. Yeah, I don't remember how that works either. Khan Academy has something. Man, which of these are at all understandable? This one. I like this one. Open image in new tab. Oh. Well, that's not useful. Ooh, I like that. That looks great. Good enough. Good enough? There we go. I do recall there being water in this one. Very vaguely. You guys are up against way tougher tests than I ever wrote, as far as I know. Okay. HGOAC. mercury oxoacetate? I don't know. But the Hg has a plus charge on it. That does imply to me that there's going to be an attack from the double bond, which has electron density, onto the positively charged thing. Attack. What does it do? It attaches itself to the terminal carbon. Oh, it's one of those brominium ion style things. I'm only bringing this up so I can show you that this is similar to something that exists elsewhere. When an alkene attacks bromine, here this would have been cyclohexene, and then you have a double bond opening up to attack that bromine, you kind of end up with a half bond to bromine from each of the carbons. And it's a high energy state because at this point they all have kind of a positive charge, like a positive formal charge, I guess you could call it. Maybe not these carbons, but whatever. The point is that that's not stable. It ends up looking something like that. That triangle reminds me explicitly of the triangle formed here. You've got your double bond opening up to attack something that is slightly positive. You'd probably get away with drawing dotted lines for each of those two things. I wonder if I can draw something like that for you. Now that leaves a slightly formal charge on, well, technically both of the carbons, but you might only have to consider it for the non-terminal one. And a water attacks it. Then another water steals it away, and you just end up with the oxygen. What's the point? How are we doing out there? I want to know how many chiral centers are present in the structures. To count chiral centers, I really just go through each individual atom and I ask myself, do I have 4 different things attached to each carbon? I actually count it manually. I've also been wrong before. There's something about resonance structures and chiral centers that I don't know anything about. Oh, and then you reduce the oxymercuration straight off. Just chops itself. Pop right off. There's the OH. That's good stuff. What do we have here? HgOAC2. The OAC leaves. I like this one better. This one's showing the flow of electrons a little more clearly, if you ask me. Don't leave. Ah, come on. Ah, nuts. Okay. HgOAC2. This Hg has a lone pair and 2 covalent bonds. That doesn't imply to me that it has a positive charge, but when anything approaches a double bond, London dispersion forces can cause it to become slightly delta plus. HgOAC2, OAC, or that acetate ion probably, is a great leaving group, just pops right off and accommodates that double bond having broken itself open. Yeah, this one shows the brominium way more. And again, it's not brominium, it's probably like mercurinium or something. You end up forming this triangle. That opens up a carbon to be ripe for attack from the other direction by anything that has a lone pair. Water is a common one, and then water can steal an H away from a formally charged oxygen as well. I like it. All the mechanisms I'm finding kind of glaze over how the reduction happens. As I recall, reduction reactions are too complicated for them to ask you about. You just say it reduces it and it's gone. Chop it right off and you're done. To remember this mechanism, compare it with adding Br2 across an alkene. Assuming you have to know the bromination of an alkene. Brominium, which is the triangle formed by 2 carbons plus bromine, is very similar to the triangle formed here. 2 carbons plus mercury. One of those carbons gets attacked. And the other thing I kind of recall is that it attacks it from the back side. Like, the water is attacking from the opposite side as the Hg is on. Because it can't attack from the same side, that collision path is blocked. I'm not going to call that an anti-addition because I'm not exactly confident. Yeah, this article does not say anti anywhere. Therefore, it might not always be anti. It's probably because you're not adding something to both of the carbons. You're eventually just chopping this one off. And it's by a particle that has a lone pair on it. Here it's the lone pair of the oxygen atom. In the bromination mechanism, it's a Br- ion. It's just such a similar mechanism. It's kind of like memorizing 2 mechanisms at once. Just throwing it out there. Clemensen. Okay, I'm going to move to Clemensen reduction. Yeah, I don't know anything about that either, so thanks for your patience. I can see what's being written in the chat. What do we have here? Why is acetylene used for welding? Yeah, acetylene's used because you can get a lot of energy out of oxidizing or burning it, and you can store it really efficiently as well. Is there a difference between using hydrogen, platinum in ethanol, and tin dichloride in acid with OH minus? No, I have no idea. I don't know how to pronounce that name, even though my wife is Polish. At this person, I have no idea, honestly. Thank you for spamming the chat with it, though. It does help you get noticed, I suppose. What are we doing here? Clemensen reduction. I don't know what that is. Zinc, mercury, amalgam or something? I vaguely remember hearing about this. I don't think I had to know this one when I was in school. The Clemensen reduction allows the deoxygenation of aldehydes or ketones to produce the corresponding hydrocarbon. So you're just chopping off the double bonded O and replacing it with 2 H's. The substrate must be strong or stable. It is complementary to Wolff-Kishner, which is strongly basic. Acid labile molecules should be reduced. Well, yeah, that makes sense because you're putting a strong acid in there. So if there's any portion of your molecule that is susceptible to attack by acids, you're going to have a bad time. The reduction takes place on the surface of a zinc catalyst. Clemensen reduction. Overall, replacing double bonded O with 2 single bonded H's. Cannot have groups which are reactive with acid on your molecule anywhere else. Unless you want them to react, that is. Okay, here we've got electrons from a metal attacking the carbon. Are they? Is that supposed to be an arrow? The double bond, the electrons from the double bond attack the zinc. I think I probably would have written that as this lone pair attacking the zinc and then the double bond breaking apart to replace the lone pair. I'm not confident there's an actual difference there. Oh, and then there's a radical? What? I'm skeptical. If there's a radical written there, they don't feel like they think it's important enough to mention that. What are people saying in the chat? Sag. Yeah, I don't know what that means. What would be the video exercise supplement for the textbook you discussed? Oof, I have no idea. I don't even know if it comes with one. That's the mechanism we just saw. Is there an actual radical formed here? No. No, there's not. Here we have the ketone attacking the hydrogen of the acid first. And there is a radical formed there. Fun. Wow, I'm getting lost here. So you form you could call it covalent-ish bond. It's probably more of an ionic bond, but whatever. Between the oxygen and the zinc. A single electron. A single electron donates itself to the carbon to keep it neutral? It's like a tertiary radical. Tertiary radicals, and I mean that as this is a carbon with 3 things on it and a single electron. Like, they're a little stable. Certainly more stable than, like, primary radicals, but I'm still surprised. Then you lose ZNO. This makes no sense to me. I don't like it. That's not it. That's just a picture of a cat. Whoa, I'm in over my head on this one. I'm abandoning this. I don't know if I can explain Clemensen very well. Looks to me like we're forming a tertiary radical. Carbon with 3 things attached plus 1 single unpaired electron. That itself is reactive, but it's really unclear to me in this particular mechanism that's written how this actually even proceeds. I don't think there's enough information written here. Reactive, but I don't know where the electrons are going. That might be as far as I can take you on that. I can try to learn more about it and crank something out for you, but right now I got nothing for you. Okay, we had a question about diastereomers. Now, my real guess here is that you're wondering about the difference between enantiomers and diastereomers. The word enantiomer is specifically for what we call non-superimposable mirror images. If I was to draw, wow, this is insanely difficult without like something that I can draw on the screen. The one you've always seen. There we go. I know your question was about diastereomers, but enantiomers are what you get when you mirror something. You've probably seen a picture of someone like holding up both of their hands, and their hands are mirror images of each other, like there's a line of symmetry straight down here. But then you can't actually superimpose them because your thumbs end up on the wrong side of the molecule. You can kind of do it this way, but you're not putting the top of your hand on the top of your hand and the bottom on the bottom. So they're mirrors, but you can't superimpose them. Diastereomers are something different entirely. They're not even mirror images. It's not like they are superimposable mirror images. If they are superimposable mirror images, they're the same molecule. If a molecule is the same as its own mirror image, it is called, I believe the word is meso compound. Correct me if I'm wrong. But diastereomers, is that how you spell that? Oh, I used the wrong letter. Diastereomers are basically not even mirror images of each other. The place that I see this come up the most is with longer chains of carbon atoms, like 3 or more, because then the direction that each of the extra groups that aren't along the chain, they could be flipped in a way that makes the two molecules not even mirrors. What you might recall is that enantiomers are distinguished in terms of naming with R and S. It's like a levorotary and dextrorotary for which direction they rotate plane polarized light or something. That's all I actually know about it. Diastereomers are easily distinguished if you've labeled all of your centers with R or S. So let me give you an example. Let's say you have a 2-carbon chain. No, let's do a 3-carbon chain. No, let's do the smaller one. Let's do a 2-carbon chain, and we're going to make it 1,1-difluoro. No, then that's not. 1,2-difluoro, 1-chloro. I have no idea what I'm doing. 2-iodo-ethane. Okay, all I'm trying to get across there is that you have like FCl on one carbon, single bonded to an Fi on the other, so that each of the carbons has a chiral center. And to the person who asked about chiral centers, I'm just making sure that this carbon has 4 different things attached to it. Oh, wait. Oh, my lord. I must have forgotten H's here. There we go. So this carbon has an F, a Cl, an H, and another carbon attached to it. That's 4 different things. Therefore, it's a chiral center. This carbon has a carbon, hydrogen, fluorine, and iodine connected to it. So that's 4 different things as well, which means that there's 4 different configurations for this molecule. This molecule could be RR, RS, SR, and SS. RR and SS are mirror images of each other. And I know that because I literally just flipped the chirality of both. RS and SR are mirror images of each other. Cool. RS and RR are not mirror images of each other. See how RS flipped to become SR because you're flipping the chirality on each of the centers? R becomes S, C. And this S becomes R. You're flipping the chirality on all of the centers, therefore they become and are mirror images of each other. But if you flip the chirality of one center and not the other, all of a sudden they're not even mirror images of each other. And so relative to each other, they are diastereomers. You can play that game with SR and RR as long as they aren't exactly in reverse of each other or like exactly flipped. They are not mirror images of each other either. You have to flip the chirality on all of the centers for them to be mirror images. If they are not mirror images, they are not diastereomers. That's really what I'm trying to get at here. Cool. Cool. I cannot answer questions about whether or not diastereomers or enantiomers are made in any particular reaction. I'm just not good enough at organic chemistry to help you with that. I see it written in textbooks all the time, but nah. Okay, last I'm going to do inductive effect. Then I'm going to go back through the chat and see if there's other topics that I've missed. This is the last one that I have written here. Now, I'm not here to lie to you. I was never good at the inductive effect. I vaguely remember it. The inductive effect, doesn't it play a role in like reactions of benzene or something? Ortho and para directing? No, I'm lost. Like, I know what that means, but I never memorized this. This does not explain what inductive means. A substituent on a benzene ring can affect the placement of additional substituents. Okay, so if you've already got something attached, electrophilic substitution will give you something special depending on what that thing is. How do we know where an additional substituent will most likely be placed? The answer is inductive and resonance effects. Inductive effects are directly correlated with electronegativity. Substituents can either be meta-directing or ortho-para-directing. Ortho-meta-para. The first scenario for adding an electrophile is when the substituent is an electron-donating group. Anything that has a lone pair of electrons on the atom directly bonded to the ring. So like oxygens, nitrogens. Not sure why alkyl groups count, but that's okay. Electron-donating groups cause the second substituent to add on ortho or para. Oh, interesting. Okay. Okay, if an electrophile is added to the monosubstituted benzene ring in the para position, these are not as stable. Great. Therefore, the major products are ortho and para. Para is slightly less common due to steric hindrance. Sorry, slightly more common. Electron withdrawal, though. How does that para direct? So here's what I'm looking at and kind of understanding. I remember that for electrophilic substitution on a benzene at all, the reason it can happen is because there are resonance structures in the transition state. Like, even if the CH3 wasn't here, the electron pair from benzene attacks the electrophile, but you end up with a carbocation. As in, that carbon only has 3 bonds and it has nothing else that it can bite onto yet. But that plus charge is distributed around the ring. And what I remember is that the positive charge kind of skips to alternate carbons, especially in a 6-membered ring. So the positive charge on that carbon can skip 2 carbons away and end up 1, 2 over here. And then it can skip another 1, 2 away to here. Then it can skip another 1, 2 away, and you're all the way back here. So when you have the carbocation on one carbon, that positive charge can also be drawn on alternating carbons around the ring. What I'm reading here is that what they call electron-donating groups, which you just have to memorize as alkyls or things that have oxygen or nitrogen directly attached to the ring, those can help donate electron density to the positive charge that's formed, and therefore it stabilizes the positive charge and makes it more likely that the electrophile could have been in the ortho or para position. Electron-donating groups stabilize the carbocation that's formed and therefore the electrophile is likely to have attached either ortho or para, because that's what forces the positive charge to be on either the metacarbons or the carbon with the electron donating thing itself. I feel like I learned something there. Maybe I could help write that down for you in some kind of note, right? Electron donating groups, which they explicitly say are alkyl groups. I'll just make a list here for you, like methyl, ethyl, propyl, alkyl, etc. Or if O or N is connected to the benzene ring directly, force electrophiles. Now, what are electrophiles that might attack? They just drew it as E here. I don't want to just use a letter E. I want to be able to give you some examples. I search list of electrophiles and it gives me a pile of nucleophiles instead. That's fun. There we go. Oh, halogens. Oh, right. Electrophilic substitution. We always go with, like, bromine for something like that. Do these all have something in common? They all kind of have positive charges. Br2 counts for that because you can London dispersion force your way into having a slightly positive bromine atom. This is very unclear, this picture, but that's okay. Directly force electrophiles to attach on the ortho or para carbons because the group donates electron density to the carbocation that forms, and this makes the product transition state more stable. So, aniline, which I believe is a benzene ring with an NH2 group on it, plus Br2, will either give you ortho bromoaniline or para bromoaniline. Because the N can donate its lone pair to the carbocation intermediate. Oh, it's the word intermediate. That's the word I'm looking for, not officially transition state. This makes the intermediate more stable. Can donate its lone pair to stabilize Cool. Okay. I like that. I like that. Methoxybenzene. C6H5OCH3 plus, I don't know, which of these would actually end up getting used somehow? Is that like tert butyl lithium or something? I don't know. What do you have to attach to that carbon to make it stable? You can tell I'm not good at organic chemistry. I have no idea how you would even attach some of these. I'm just going to use Cl2 then. Thanks for being with me. Your patience in dealing with my inability to do organic chemistry is directly benefiting everyone who will get this same thing next year. Yeah, someone just asked me to share the document. There you go. There's the link to it. Oh man, the chat's been blowing up and I haven't been reading it. Wish me all the best on this 9th of July. Yeah, sure, good luck. Let's say we have, what the hell is that? Oh, it's like an imine. Can you explain nucleophilic attack, lone pair, partial positive and negative, and the action mechanism? Diastereomers contain at least one or more of same structure on a mirror image. I don't know what that means. How do you identify the chiral center in cyclic compound? Oh, in cyclic compounds, that's trickier. If I feel like I answered this, inductive effect, the electron donating groups are ortho and para directing. At least that's what they call them. Let's take a guess and say electron withdrawing groups cause electrophiles to attach to the meta carbon for the opposite reason. Now let's go see if that's true. On the electron withdrawing group, the second substituent adds to meta. This can be explained because the carbocation that forms it's not likely that the positively charged carbon in the carbocation would want to be next to a delta positive carbon. So it's not exactly the opposite reason. The carbocation intermediate that would be made if it added to ortho or para is unstable because it wouldn't want to be near, oh come on, wouldn't want to be near a slightly positive charged carbon atom. I'm not confident that I answered that very well, but perhaps something that I said. Deactivating. I hate the word activating because I don't feel like it really gets across what's happening. Like, activating definitely means that you'll get a lot of ortho and para and hardly any meta. Strongly deactivating means you get a lot of the meta product. These are written in a particular, like along a spectrum, because this is where you get more orthopara. This is where you get more meta. And then along the spectrum, you get like the fraction of product that might be one or the other becomes more equal, I suppose. So an extra phenyl group or an extra fluorine group, you're going to get about half and half-ish, I guess. I don't know. I'm guessing and making things up. So cool. That might be all I can do there as well. What can you do? Okay, let's go to the chat again. Let's see what the people are asking for here. Joseph says, never study last minute. Good luck. Modern day usage. How many chiral centers are present in these structures? Right. You've been very adamant that we need to cover how many chiral centers there are. This is just that's a crazy amount. Chiral centers in cyclic and non-cyclic molecules. How to count chiral centers. Note. If there are valid resonance structures for your molecule, this rule that I'm about to give you won't work. I think I've been catching flack on my chiral center molecule because I picked caffeine. And I said one of the caffeine has no stereoisomers. There are no tetrahedral structures. Okay, it couldn't have been caffeine then. Maybe it was testosterone. That's not me, but I'm sure the error is common. So when I'm looking for how many chiral centers there are in a molecule, I'm going through all of the different carbon atoms and seeing if I have 4 different things attached to it. It has to be a full 4. Any duplicate things make it not chiral. I think it's probably better if I just steal this. Let me try something out here. Let's see if my computer just decides to quit for no reason. There we go. Okay. auto capture. I'm trying to bring up a thing that is like a picture so that I can draw on it for you. Whatever. Guess I'll just do it another way. Too bad. So sad. There you go. Too bad. Insert. Drawing. New. Beautiful. Now you can see this molecule. Okay, so the question we're asking ourselves is, how many chiral centers are in this molecule at all? So we're going to go through these one by one and decide whether or not they actually are chiral. Let's see what I got here. Do I have like an X or a check mark I can put through here? Yes, I do. That's fun. Okay, this carbon here has a double bond to an oxygen. So first of all, it's not even a tetrahedral center. This carbon is attached to a carbon atom here and then a bunch of other stuff. It's attached to a different carbon atom here. And it's a different carbon atom, so those technically count as different groups. But it's also doubly connected to this oxygen. It's not even connected to 4 different things. Therefore, it is not a chiral center. This carbon is connected to a CO and a CH2, but it has 2 H's on it as well. Those H's are not shown, but it is connected to them nonetheless. There we go. So it is not a chiral center either. Again, with this carbon, it is connected to 2 H's. The H's are not shown, but it is connected to them. Now this carbon's exciting. This carbon is connected to a CH2CH2CO. This carbon is connected to a C that splits off into a double and single bond. This carbon is connected to a C that is split into a CH2 and a CH. And it's also connected to a CH3. This also answers your question about in-cyclic molecules. In order for it to be connected to 2 different groups, you'll have to follow yourself all the way around each ring, and it has to be identical at every single point, all the way back to your starting point. It's not enough for it to be 4 different atoms, like carbon, nitrogen, oxygen, fluorine, or whatever. This carbon, for example, is connected to 4 other carbons. But each of those carbons is very different from each other. This is a CH2, which is connected to more carbons. This is a CH3. This is a CH. And actually, this is a C that is double bonded to another C, which was not like any of those other carbons because there was no double bond there. This is our first example of a carbon that is chiral. Just trying to find the symbol I'm looking for. That one ends up being chiral because it's connected to 4 different things. Great. I'm using green circles for like, yes, this is it, and this strike through symbol for no, it's not. This carbon is connected to a C and an H, but then it's double bonded to something else. As soon as it's double bonded to anything, it cannot be a chiral carbon. Again, this carbon is double bonded to something, therefore I know it's not. This carbon has two H's on it, therefore it cannot be. And I can go around the ring actually and identify a bunch of those. That was a CH2 group. This is a CH2 group. I know it's a CH2 group because each of those only has two bonds written, which leaves two extra unshown bonds to lead to hydrogens. This one can't be chiral. This one can't be chiral. And this technically counts as a carbon, but it's the end of a methyl group or a CH3 group. Therefore, it is not either. And for the same reason, I'm going to say that this one's not. Cool. Okay, let's look at some of these other centers. This is connected to four different things. There is a hydrogen not shown. That's one. You've got a CH2, CH2 quaternary carbon. You've got a CH, or tertiary carbon here. And you've got another quaternary carbon here. Oh, that's interesting. Oh, no, it's not. This carbon is connected to a CH2 here, a CH here, a quaternary there, and an extra H. Those are all very different things. It is not identical in any of those two directions. As soon as you start to appreciate that there's not much symmetry in this molecule, you might start to see where some of these chiral centers come from. This carbon is connected to a tertiary carbon here, a hydrogen that's not shown, a CH2 group here, and another tertiary carbon, but this tertiary carbon is part of a pentagon, and this one is not. So they are not identical carbons either. Those are different groups, even though they're both tertiary carbons. So it's also chiral. This carbon is connected to a CH2, a quaternary, a tertiary, and a hydrogen that isn't shown. All different groups, therefore chiral. Am I making a mistake here? No, I'm not. This carbon is connected to a CH2, a tertiary, a carbon that has an OH on it, and a CH3, or primary. Those are all very different, therefore it's chiral. This carbon is connected to an OH shown, an H not shown, a CH2 here, and a quaternary here. Those are four different groups as well, so it is chiral. Very nice. I'm going to save and close that. I don't know if that was helpful for you or not, but this is the definition of a bunch of cyclic molecules all connected to each other. You won't necessarily be able to come back to the notes to see, but you can always come back to the video, I suppose. I've discovered that when I do a live stream, it just gets posted to my channel anyways. It's probably notifying you about it too. Okay. Nucleophilic attack, lone pair, partial positive or negative. You know what? I am going to do a little bit of that because I feel like it'll help carry some people through organic chemistry. How do you identify R or S? That was the toughest question in like second year chemistry for me. Secondary, since you have two carbon atoms, if you had three for tertiary and one for primary. Yeah, that's correct. Lajpat, this pH stuff, I'll just schedule an acid-base one to do. Lajpat, tell me when your acid-base test is, secondary, my guy. I assume you're talking about the nitrogen guy who was asking about the imine earlier. Alcoholic KOH with alkyne halide. Oh, I'm lost. I don't even know what that means. Nucleophilic attack. Yeah, I can go through a couple of these. A carbon that is attached to an electronegative, wow, that is not how you spell electronegative, atom, is slightly positively charged. The electronegative atom attracts electron density away from the carbon atom this leaves a partial positive on the carbon itself. Now in organic chemistry, for those of you who are doing more advanced mechanisms, this is most common for a CO or carbonyl group. The carbon here, I notice in mechanisms, gets attacked by slightly negative things. That can be double bonds. It can be OH minus ions, etc. all the damn time. But nucleophilic attack also plays a role in SN1 and SN2 reactions as well. When the electronegative atom is part of a good, well, often when it's part of a good leaving group, like iodine is. Iodine is slightly electronegative, therefore can steal a bit of electron density away from carbon. Fluorine is the most electronegative and will leave carbon with an even more positive charge. So for those of you doing advanced mechanisms, you're going to want to look at that bit right there. If you're talking about nucleophilic attacks, like the backside attack, SN2, and you're thinking more along the lines of like CH3I getting attacked by OH minus, that carbon has a slight positive charge, or delta plus, because it's attached to an... is iodine electronegative enough for that? I'm going to use bromine because it's a better example. Bromine's more electronegative than carbon. Therefore, it gets a delta minus, because there's polarity in that bond, and the carbon is left with delta plus. So the OH ends up attacking the carbon. It's still connected to its 3 hydrogens. And then the Br is kind of getting kicked off at the same time. But the Br is inviting itself to get kicked off because of the delta plus that it's leaving on carbon. It's the minus charge on the OH minus that attacks the delta plus charge on carbon. This reaction here is an SN2 reaction. The 2 here is for bimolecular. You have a collision between the OH minus and the CH3Br. The N is for nucleophilic, and the S is for substitution. But the explanation here is that bromine is more electronegative than carbon. So bromine steals electron density away from carbon in the CBr covalent bond. Wow, that's not what I typed again. This leaves C with a delta plus charge. I'm going to go and get the delta symbol so you know exactly what I'm talking about. And Br with a delta minus partial charge. That, in turn, makes the carbon an attractive target for the O lone pairs of oxygen to attack. Very nice. Now perhaps you're also, oh no, I closed it. It's okay, I guess I have a link to it here, don't I? Yeah, we're losing some viewers, that's totally fine. You know what you need to study better. July 26th, my test is acid-base pH. Lajpat, I can promise you I'll do an acid-base mega thing before then. I can do a live stream where we just go through a bunch of questions. 90 minutes. What is a positive indicator of iodine test for unsaturation? I'm motivated to study again. Yeah, sure, good. That's what I'm here for. We'll just be motivating for you. If anything, I'm demonstrating that not everyone knows everything, clearly. Come on, computer. Okay, we take a 5-hour break here while my computer loads. How's everyone doing? Tell me in the chat how you feel on the inside. Yeah, lots of people saying thank you. You're welcome. I'm going to keep going for another 15 minutes or so here. Go study. Be good. Do good work in the world. There you go. Now, I guess the other thing that I'll mention here is that if you have lots of alkyl groups attached to that carbon, notice the only difference between CH3Br and CH33Br is that I've replaced each of the hydrogens with a methyl group. That makes it so that the Br can actually just fall right off. You end up with CCH3, and that has a positive charge. And the Br has a minus charge, as bromide often likes to. Now this is the very beginning of an SN1 reaction, and it's the one for it being a unimolecular first step. It is one molecule breaking apart or decomposing into two separate things. But again, this carbon, which has a positive charge on it, you know what, I'll be even clearer and put that plus on that carbon itself, makes it an attractive target for a minus to attack. So it is actually an intermediate. It is the product of the decomposition. But then the OH minus ion will attack it. It's got an actual full positive charge, not even just a partial positive charge. And you end up with your OH attached to it. Here, the Br can fall right off of the molecule because the carbo cation that remains is tertiary. Tertiary meaning it's connected to 3 other carbons and is therefore stable. The tertiary carbocation is a full +1 positive charge. Hopefully, it's obvious. Attractive. This is obviously attractive to a minus charged particle. For example, like OH minus, which will attack it. You asked for nucleophilic attack, partial positive or negative, and the reaction mechanism. No, I guess I've kind of almost given you the reaction mechanism for these nucleophilic attacks. I should put this into square brackets with a minus charge on it. And some teachers will use a special symbol for transition state. It's kind of like an equal sign with a vertical line through it. I'll try to be clear about that so you don't fail. This is a transition state. Which, by the way, is code for very unstable and will keep reacting from there. But it has a minus charge. The OH comes in from the opposite side. You've got 2 half bonds on either side, and you end up with a minus charge. Then the OH takes over for full, and the bromine has its full minus charge. That differs from this SN1 reaction because the carbocation that is formed here is an intermediate, which is code for it's actually kind of stable. You wouldn't be able to render it as a precipitate of any kind. It just is willing to stick around a little longer. It's an energy minimum in the potential energy curve instead of a maximum like a transition state is. And, oh yeah, and the mechanisms that go along with it. Cool, cool, cool. Okay, I promised you guys I'd stick around for 10 more minutes. There's only a few of you here. Can I get reaction mechanism PDFs in my email? I have no idea. I don't have any, like, I have very basic reactions. Like, I have a PDF that I made of predicting products, but I don't have any reaction mechanism PDFs for you, I'm afraid. The next question is, what is the positive indicator of iodine test for unsaturation? This is actually, I think, the last question. If you have further ones, feel free to ask them right now. I don't know the answer to this, though, but I'm going to go find out. Iodine test for unsaturation. It specifically says lipids, but I'm sure it would work for all alkenes. A positive test is that the pink color disappears. Why would it be pink in the first place? Let's go find out. Oh, I remember the iodine test. It's like the iodine number, and it's like how many molecules of iodine react with it, therefore how many unsaturations are there. Okay, I'm opening this. Wow, this is trash. Starch, iodide, sodium thiosulfate. Weigh out the fat or oil. Add Widge's solution. 2 grams of diiodine hexachloride in ethanoic acid. Well, that's not helpful. The question is, what is the positive indicator of iodine test for unsaturation? The hottest tip that I have is that image result that actually showed me a pink color disappearing. So let's go find out. Sure, I'll open you. Okay, so it seems to me that the iodine test requires some kind of reagent that produces a pink color. I'm very unsure what would cause that, but perhaps it's the sodium thiosulfate that all of these seems to say. You're supposed to use. Positive result, pink color will disappear if it's unsaturated, and that's true whether or not you use Hubble's reagent or oh, this is just phenolphthalein and alkali. No, that's not what you asked about, though. I don't think I have anything that's particularly useful for you as an answer except this image, which you really could have just looked up on your own, right? Now, what does free fatty acid mean in this example? Is that their way of saying unsaturated? Or does it just mean they're not bonded together? I'm losing sight of what you asked about. You asked about iodine for alkenes, not just lipids. Iodine solution can be used to detect for carbon-carbon bonds. A dark brown color is decolorized to a lighter yellow. That's not particularly useful. Oh, a 19-second video. Yes, please. Okay. Iodine solution. Yes, we understand. It's got I2 in it, and some of the I annexes on. Wow, that was crap. Like, what even happened? Iodine molecules add to the double bonds. You halogenate the double bond. When this occurs, the dark brown color is decolorized to lighter brown yellow. Cool. iodine solution is dark brown. I believe, yeah, iodine solution is dark brown. I2 AQ. If there are unsaturations, specifically double or triple bonds, in your molecule, they will react with the iodine. Let's just do CH2C. You'd never get that in the liquid form, though. CHC6H5, maybe? That's not a good example. There, good enough. C6H11, yeah, that would work. Plus I2. The idea here is that this big molecule, the double bond breaks, and you end up adding an I to each of these carbons. There. Now it's a single bond, but the I2 has been used up. This uses up the iodine, and so the brown color disappears. Therefore, dark brown color of the iodine station is decolorized. That's a positive test, which means yes, you have double or triple bonds. Dark brown color does not change. Negative test, no, you do not have double or triple bonds. There's the answer to your question. This is the interpretation of results. Is not changed. Cool, cool. There's your answer. Hopefully that helped. Oh man, this is blown up. I'm looking at the chat right now. Ring expansion. I don't know anything about ring expansion. Sorry. I have an exam Friday. Will you post this live stream after? Yes, this live stream appears on the channel about 10 minutes after I close it. YouTube processes the video and plasters it right there. I made a new section on my channel homepage where the live streams go. Can anyone get an A in organic chem with an average IQ? The answer is definitely yes. You're just going to have to study a bunch, right? Practice, practice, practice. Predicting products as well as writing the mechanisms. The key bit to understand is all of the mechanisms, all of the step-by-step processes are all about finding out what's delta plus charged, and 50% of the time, it's a carbon that is double bonded to an oxygen, and finding what's negatively charged that can attack it. It's how it's going to start most of the time. I am surprised to find less people here. Yeah, well, it's organic specifically, and I even told people I don't know organic. The basicity of Drago molecule, I don't know what that means. I'll Google it, though. Can you explain the term reducing sugar? No, never heard of that either. This sounds more like biology to me. I hate biology so much. Like, I went to the University of Waterloo here in Canada because it's the only place I could study chemistry without taking any biology. Drago's rule? Someone asked for Drago. Is it Drago's rule? Nandish, can you be clearer about what you're asking? I just Googled it and I have no idea. Reducing sugar. Let's go find out. Reducing sugar is one that reduces another compound. The carbonyl is oxidized to carboxyl if it has an open chain form with an aldehyde or free hemiacetal. Oh my lord. I'm going to try something and I'll show you guys a little trick. Like, that made no sense to me. I mean, it made some sense, but I'm not really sure if I can understand that. One option is to go to Wikipedia. You guys can probably see, yeah, you guys can see the URL up here. And you can replace your language, here for me it's EN for English, with the word simple. And sometimes, it doesn't exist. But sometimes there will be a version of the Wikipedia article that's like, for lack of a better term, for like simplified. If I go to the Wikipedia article for photosynthesis, for example, it's a process that converts light energy to chemical energy through cellular respiration. But if you're intimidated by that, replace EN with simple, and it'll give you something. Photosynthesis is how plants make carbohydrates. It uses sunlight to turn carbon dioxide into sugars. Wasn't that easier to understand? Yes, it was. And look at the picture. It's much clearer. Carbon dioxide in, oxygen out. I don't think that picture was in the original. Oh, I guess it was. But a couple of these were taken out. Whatever. Okay, what do we have here? How to find the most acidic hydrogen in a compound? I don't have an answer for that. My first instinct for most acidic hydrogen is, number one, a hydrogen connected to oxygen is often acidic enough that it can be ripped off. The next thing I would look for is a carbon double bonded to an oxygen. If I have that, I look at the next carbons in the chain, and if those have hydrogens, those are acidic and are likely to be plucked off as well. Okay. Can you explain Hooke's rules in organic chemistry? I've never heard of that. Bio-orthogonal reaction. Shika, can you tell me what you're studying for? Because I've never heard of any of these. I'm willing to learn, but it would also be useful to me to know why you're asking these questions. I don't mean that in a condescending way. I'm just like, these are way above whatever I've learned, so I want to know why you are asking them. Bio-orthogonal chemistry. Like, what even is that? Any chemical reaction that occurs inside of living systems without interfering with native biochemical processes. Well, that's fun, but I regret to tell you I know nothing about biology. So no, I cannot help. And lastly, Nandish, you've said Drago again. At Nandish. Oh, it let me tag you. At you. When I Google Drago molecule, nothing comes up. So I don't know what you are asking. Do you have a link? Drago molecules? Let's Google that. There's Drago's rule. Oh, Drago molecule from Chem Academy. I'm going to put that in quotes. Drago molecule gets me only 1,000 results in all of the internet. Great idea that it might be Drago molecule. Let's see if Nandish replied. Not Drago, maybe? Drago's rule. Drago's rule says there's no need to consider hybridization if there's at least one lone pair or any of groups 13, 14, 15, 16, or central atom has a low electronegativity, or, and it's all the 4 lone pairs. Okay, but who cares? The detailed analysis of the structure formation of phosphine gives an understanding of the electrons in pure P take part in the formation of chemical bonds. Resistance for the orbitals that get hybridized. pH 3 is regarded as a Drago molecule. For the pure p orbitals that hold the electrons involved in a bond, the bond angle is nearly 90 degrees. Okay, so if there's I don't like this rule. Or do I? The electrons involved in bond formation, the bond angle is 90 degrees. Phosphine bond angle. We must not use Drago's rule here. It must be called something else. No one can agree. I've never heard of Drago's rule, and I am unable to help. Oh my lord. What are these questions? Will you have a Q&A on just general chemistry? Make a request for a specific topic, maybe, and I'll cover each of the general chemistry topics separately. Maybe? I don't know. I just find I'm finding it more streamlined for all the questions to be on one topic. You can always just ask me random questions on Facebook, Twitter, Reddit, YouTube, wherever you can find me, and I'll try to crank something out for you anyways. Nucleophilic substitutions. We've already done that today. Not sure if I covered it in enough depth for you, but I can share this document with you. And then the last thing here is another thing that I've never heard of in my life. Paterno-Bucchi reactions. Oh, this one, something comes up. I'm not going to lie, I've never heard of this. It's a 2+2 photocycloaddition. Makes an oxetane ring from an excited carbonyl and an alkene. Oh, hello. Well, this is just like a Diels-Alder cycloaddition, except it has an oxygen atom in it. Let's see. So you excite the oxygen, like this bond in here. Then presumably the oxygen attaches here. That double bond breaks apart to here. Then what? Then that's it? You just make, I guess that's called an oxetane? And it doesn't, like, the orientation of this can be flipped, so you definitely get a mixture of stereoisomers for that. That's fun. I'll make a video about that. I like that reaction quite a lot. I'll take a screenshot right now. But I regret that I can't really help. Can you explain Julia olefination? No. Can you explain nitration of indol? No. Oh, man. Now you guys are poking holes in what I know. Thank you for being with me today, but you guys are asking questions that are way above what I can even do, right? So I don't blame you for leaving. You're not going to get anything from me, I'm afraid. The last thing, sir, what are inorganic salts? Well, organic salts are probably just any particle that has a carbon chain, as well as a positive or minus charge with a counter ion. Like the salt comes from the fact that there's going to be a plus and minus charge. Yeah, the most common kind is when you have a carboxylic acid and you like chop off the H somehow, usually with a base, and then you just attach a different counter ion to it. So like when you react sodium hydroxide with acetic acid, technically the only product you get that isn't water is sodium acetate. You've taken the carboxylic acid and replaced the H with a metal cation. But you can do it for all of these, because these all have labile H's, or H's that can be plucked off. Okay, thank you for being with me. I am going to end it here. You've all given me some great content to create videos about. Not that that was the purpose of this. The purpose of this was to help you. And I hope I did that. Go study. That's what I got for you. You can ask me more questions on Twitter, Facebook, Reddit, or YouTube. Anywhere you can find me, just send me questions. I'll do my best because I'm here to help you. And I have the summer off. Why does the electron go from pi to pi star and not from non-bonding to pi anti-bonding? That sounds like a molecular orbital question that I'm not good with molecular orbitals, especially when it comes to two atoms that are not the same. I'm not good at that. Specifically, I don't know anything about it. A session on inorganic. I might know even less about that. Okay, you guys are free to go. Don't feel like you have to stay. Just close the window or whatever. Ayushi, I don't exactly even know what your inorganic chemistry topics would be. Do you mind saying in the chat what kinds of things you would want covered in an inorganic session? under what conditions can a high-grade alcohol give low permanganate time test? I've never heard of the low permanganate time test. Oh my lord, am I the worst chemist of all time? I must be. What's the permanganate time test? Permanganate time is for oxidizable impurities in ethanol, acetic acid, and stuff. Well, that's fun, but I'm going to have to learn about it before I answer anything. Amazing show. Hey, I appreciate that. I'm really just here to answer whatever questions you guys have. I'm in Streamlabs. Okay. If you need anything, please let me know. You can message me again. Facebook, Twitter, Reddit, or YouTube. You want something, I'll give it to you. Go to my community tab and just ask for stuff. Can we separate a protein using resins? You should learn more, though. Yeah, no kidding. Apparently, I don't know any of what you guys are doing. I assume you were all studying for JEE